So what happens if we combine two or more springs together? So will the system of the spring be harder or softer? So let's explore this. We have the two types of the combinations mainly, okay? The first one is called the series combinations, and the second one is called the parallel combinations. For the series combination, so we just put one end of the springs, right, combined together like in this picture. Okay, so just like this picture, and then if we try to pull the spring, okay, the right hand side of the spring to the right with the force equal to the F. So one keynote that you need to remember is that, okay, is that if we connect the spring in the series combination, it means that the force on each spring must be equal to each other. Okay, so let's mean that the force on each spring must be equal. Okay, the force on each spring must be equal. So it means that the spring K1, right, we just get the same force F, and the spring K2 we get the same force F as well. Okay, so then how about extension, right? So let's say that, okay, let me just write equation first. So we can say that the x equal to the x1 and then plus the x2. The x1 is what? The x1 is the total extensions, right? The x1 equal to the x is the total extension, and the x1 is what? The x1 is the extension of the spring 1, and then plus the x2, which is the extension of the spring 2, right? Making sense? Because if we try to pull the system here to the right hand side, right, so it means that both of them must be extended. So that's why we can just compute the total extension to be the summation of the extension of the spring 1 and the extension of the spring 2 here. But then we know that, okay, we know that because each spring we get the same force, right? So we know that the F equal to the K1 and then times the X1, right? And also we know that the F equal to the K2 times the X2. Okay, so don't forget that the extension of the spring, right, it just depends on the external applied force. We talked about this question already from no, from the other chapters, not this one, right? Okay, that's fine. Okay, so now if we plug in the x1 and the x2, right, into this equation, so let's see, we can get that the x, right, is gonna be equal to the F and then over the K1 plus the F and then over the K2, okay, all just equal to the F and then the 1 over the K1 plus the 1 over the K2. Okay, so now you can see that the F is the applied force, right, and the X is the total extension. So then in this case we can think this term, right, we can think of this term to be the 1 over the, let's say, the K series. Okay, so it means that we can get the equivalent, okay, spring constant for the series combination as as 1 over the K series equal to the 1 over the K1 and then plus 1 over the K2. Okay, but if we have more than the 2 springs, right, connected in the series together, so you can just add more spring into this one. Okay, and that's it. So now we can get this equation, right, the equivalent spring constant for the series combinations in this case. Okay, so what does it mean? It means that we can just replace, the system of the spring, right, by only one spring having the spring constants equal to this value, and that's it. Okay, so let's just try to plug in the number, and you can, and let's see what do we have. Okay, let's try to plug in the number. So okay, if we try, let's say that the K1 equal to maybe the 6.0 Newton per meter, and the K2, right, equal to the 4.0 Newton per meter. Okay, so let's see. Then we have that the 1 over the K series equal to the 1 over the K1, right, 6.0, and then plus the 1 over the K2, which is the 4.0. Okay, so now we just want to solve for the K series, right? We can just, do the cross multiplication here. We have the 4.0 plus the 6.0, and then over the 4.0 times the 6.0. Okay, so this equal to the 10.0 and then over the 24, right? Then finally we can get that the K series must be equal to the 24 and then over the 10.0, right, just equal to the 2.4 Newton per meter. So it means that if we have the 2 springs, right, with the spring constant K1 here and the K2 here connected in the series, then we can just replace these 2 springs by one spring having the spring constants equal to 2.4 Newton per meter, and then it's going to work as the same as the 2 springs here. Another thing that we should that we should consider, right, is that, okay, so let's notice the number. K1 is 6, K2 is 4, but now for the series combination, right, the equivalent spring constant equal to the 2.4. So you can see that the 2.4 here is less than the 6 and the 4, right? So it means that when you combine the 2 springs, right, or more in the series combination, the equivalent spring constant, right, for the series combination must be less than the minimum value of the K1 or the K2 and etc., right? So it means that, okay, let's compare here. K1 is 6, the K2 is 4, right? The minimum value of these two is equal to the 4 Newton per meter. So it means that the K series must be less than the 4 Newton per meter. So we just showed it already that it's just equal to the 2.4. Okay, so that's the series combination. So then how about the parallel combination? Okay, so now for the parallel combinations, it means that we have the K1 and the K2, right? We have the 2 spring K1 and K2, And then if we connect both ends together, okay, so it means that both ends of these two springs, right, just connected together, and both ends here just connected together as well, right? And we apply some force F to the right hand side. So one thing that you can see from this picture, right, is that the extensions, right, of both spring must be equal. Okay, so it means that both both of the springs, right, which extends at the same length. Okay, so then what's going to be different, right? The applied force on each spring is different. Okay, so we can just say we can just write down as the F equal to the F1 and then plus the F2, right? F equal to the F1 plus the F2. Actually, it's just the free. Okay, we can just see this one from the free body diagram of this object, right? Because if we have the F to the right hand side, so we can say that we have the F1 here and the F2 here exerting on this object, right? So we can say that the F equal to the F1 plus the F2. So it means that if we just write down the free body diagram of the spring, right? So we can have the F1 to this direction and the F2 into this direction, which is the applied force on the two springs here. Okay, so we can say that the F, right, is going to be the total applied force. Okay, it must be equal to the applied force on the spring 1 and then plus the applied force on the spring 2. Okay, so this is what we get, right? Okay, so now again, right, let's just plug in equation. We know that the F1 equal to the K1 and then times the X, right? So don't forget that the extension just the same. So that's why you have the F1 equal to the K1 times the X. And then also we have the F2 equal to the K2 and then times the X. So now we can just plug in the F1 and the F2 into this equation. We have that the F equal to, okay, so now K1 times the X plus the K2 and then times the X, right? Okay, which is equal to, so now the X, right, extension just is the common variables for these two terms, so we can just take it out. So it's just equal to the K1 plus the K2 and then times the X, and that's it. So now you can see that this equation, right, it just have the same form as the F equal to the K times the X, right, where the F here is the total applied force, the X here is the total extension, and the K1 plus the K2, we can think about this one as the, okay, so let's say that it's called the K parallel. Okay, so let's call it the K parallel. Then we have that, okay, okay, the equivalent spring constant for the parallel combination is, okay, is okay, so the K parallel equal to the K1 plus the K2 for the two springs, right? But if we have more than the two springs, we just add it up. something like this. So one thing that you can see from this question is that when we combine, the K1, K2, K3, etc. together, right? So it means that the K parallel must be greater than this value, okay? So we can conclude that the K parallel must be greater than the maximum value of the K1, K2, and etc. Okay, so this will be different from the series combination. For the series combination, the spring constant, right, must be less than the minimum value of the K1, K2, and etc. But now for the parallel combination, the spring constant must be greater than the maximum value of the K1, K2, and etc. here. Okay, so let's consider these examples. Okay, now we just want to calculate the angular frequency of these oscillations, right? So we have the three springs. We have the K1, K2, and the K3. The K1 and the K2 are connected in the parallel, and the K3, right? And then later on just connected in the series with the K3, okay? If we just want to find the angular frequency of these oscillations, so we can use what? We can use the omega equal to the square root K over M. So we know the mass M already equal to 2 kilogram. But the thing is, we need to find the K, okay? We need to find the K of the whole thing here. Okay, we need to find the K of the whole thing here. So, how, right? We can simplify this, okay? So let's consider the parallel combination first, okay? Let's consider the parallel combination. Okay, the parallel combination. Okay, so we said that the K parallel, right, just equal to the K1 plus the K2. So in this case, let me just write down as the K12, okay, to represent 1 and the 2 here. The K12 equal to the K1 and then plus the K2. Equal to, okay. Now for the K1, oops. For the K1 is the 4.0. And then plus the K2 is the 6.0, right? So it's just equal to the 10.0 Newton per meter. So this can be the parallel combination of the K1 and K2, right? Just equal to the 10.0 Newton per meter. Okay. So now our spring, right? We just look like this. So let me just make it as the gray. Okay, so now we have this spring and then this one, right, just connected in the in the series. Okay, so we have the gray one, right? The gray one is just equal to the K12, okay, and the red one is just equal to the K3, okay. So now we can just combine these two as the series combination, right? So let's consider the series combination of the spring K12 and the spring K3, okay? So then, okay, for the series combination, so we said that the 1 over K1 plus the 1 over K2, etc. Then in this case, we can see that we can have that, okay, 1 over the K let's say just normal k, right, equal to the 1 over the k12, and then plus the 1 over the k3. So now let's put in the number. 1 over the k12 equal to the 10.0 Newton per meter, and then plus the 1 over the k3 equal to 15 Newton per meter. Okay, then we have, okay, the 15 plus the 10.0, and then over the 10.0, and then times the 15, right, which is equal to, okay, so the 15 plus the 10.0, but this one has the 2 same figures, this one has the 3, right? So when we combine together, we're gonna get the 25, okay, just 25, not the 25.0. And then over, okay, so we have the 10.0 times the 15, but the 10.0 has the 3 same figures, the 15 has only the 2. So then finally we have only the 150, okay. Then finally we can get that the k here equal to the 150 and then over the 25, right, which is equal to the 6.0 Newton per meter. So this gonna be the equivalent spring constant, I mean for this 3 spring, right? Okay, so we just want to find what? We just want to find the angular frequency of the oscillations. Okay, so let's compute. Okay, so let's compute the angular frequency. Okay, so we have the spin constant of the system already, and we have the mass of the system equal to 2 kilograms, right? So then we can use the omega equal to the square root of the k and then over the m. So now the k here, right, just be the spin constant of the whole system. So it's just equal to the 6.0. And then over the mass is equal to 2 kilograms, right? So the 2.0 and then square root. Okay, so the answer is just the 1.7 radian per second. So this is answers.